Hello, these are some results of the project entitled Fluorescence Sensing of Metal Species using Co-Polymerized Graphitic Carbon obtained from melamine and urea precursors. As we know, heavy metal ions have become common toxic pollutants of water bodies which can cause several diseases and affectations to the ecosystem. Therefore, the development of new simpler and faster detection methods is of great interest to the scientific community. Recently, the graphitic carbon nitride has been reported as a good candidate for the fluorescence sensing of these ions due to its excellent stability, non-toxicity, high quantum yield and low cost. This material can be synthesized from nitrogen-rich organic precursors as urea, melamine, cyanamide, among others. The hypothesis of this work was that the different precursors used to synthesize carbon nitride powder have direct effect on the properties of the powder of graphitic carbon nitride obtained and its capability on sensing applications. For the synthesis, different amounts of melamine and urea were used to produce graphitic carbon nitride, which was further used for the fluorescence sensing of iron 3 and silver ions, as well as chromium 6 species. According to the X-ray diffraction, all samples exhibit two diffraction peaks located at 13.1 degrees and 27.3 degrees in 2 theta, which are attributed to the repeated tris-triazine units and to the stacking of the conjugated aromatic system, respectively. These diffraction peaks can be indexed to the 100 and 200 diffraction planes of the graphitic carbon nitride, according to the powder diffraction file 87-15-26. Moreover, the intensity of the diffraction peak at 27.3 degrees decreases as the amount of urea precursor increases, indicating an increase in the degree of exfoliation of the layered material. From FTIR, the bands at wave number of 805 to 880 can be assigned to the out-of-plane breathing mode of nitrogen-hydrogen and the breathing mode of the triazine rings. The bands around 1240 to 1650 correspond to the stretching and rotation vibration modes of simple and double carbon-nitrogen bonds, while the bands at 3000 to 3700 are associated with the NH and ZnH2 groups. The graphitic carbon nitride samples were also examined by UV-OVIS diffuse reflectance spectroscopy to evaluate their optical properties. The UV-OVIS spectra of the samples show strong absorption in the visible region. And a hypsochromic effect can be observed for urea-based samples compared to melamine-based samples, attributed to a lower conjugation during the polycondensation process. Furthermore, such hypsochromic shift may be a consequence of quantum confinement effects resulting from the different particle sizes and geometric limitations to the electrons in the materials. The fluorescence analysis of graphitic carbon nitride samples excited at a wavelength of 250 nanometers show three characteristic emission bands at 371, 436, and 459 nanometers, which are assigned to the electronic transition of sigma star to nitrogen lone pair state, and pi star to pi transition. The 10% urea sample was used to evaluate several metal species at a concentration of 50 micromolar. The PL spectra show significant changes in the maximum emission of graphitic carbon nitride in the presence of different metal species. According to these results, the semiconductor shows good selectivity for iron 3 and silver ions, as well as for the chromium 6 species, whereas the other metal ions showed little or no quenching effect. As can be noted, a decrease in the fluorescence emission of around 37, 50, and 70%. The sample synthesized by melamine as a precursor shows an irregular morphology based on bulk material. Similarly, the 10% urea sample exhibits irregular shapes, characteristic of a bulk graphitic carbon nitride prepared by calcination of melamine. Instead, a clear exfoliation of the layered material can be appreciated in the 90% urea and 100% urea samples. These morphologies are in good agreement with the discussed results of XRD and FTIR analyses. The linear relationship between fluorescence intensity of the 10% urea graphitic carbon nitride sample excited at a wavelength of 250 nanometers, and the concentration of iron 3 ions in a concentration range of 0 to 100 micromolar, shows a correlation coefficient R² estimated at 0.9921 and the limit of detection was calculated at 7.2 micromolar. The sensing of silver ions in a concentration range of 0 to 100 micromolar shows a linear correlation coefficient R² of 0.9885, and a limit of detection of 8.4 micromolar. The linear regression between the chromium-6 concentration and the I0 to I ratio in a concentration range of 0 to 100 micromolar yielded a correlation R-square coefficient of 0.9979 and a limit of detection of 1.9 micromolar. In summary, several graphitic carbon nitride samples were successfully synthesized by thermal polycondensation from mixtures of melamine and urea. Improved fluorescence detection of metal species can be achieved by using a mixture of precursors to obtain graphitic carbon nitride. The 10% urea sample was used for metal ion detection according to its higher luminescent properties, achieving limits of detection of 7.2, 8.4, and 1.9 micromolar for iron 3 ions, silver ions, and chromium 6 species, respectively. Notably, our graphitic carbon nitride is prepared by a simple, inexpensive method and does not require complex synthesis processes.